Welcome to our Asteroid Day 2020 digital panel on how we discover near-Earth objects. Back in December 2014, simultaneous press conferences in London and San Francisco announced the launch of Asteroid Day by reading out the 100 times asteroid declaration. That document called attention to the fact that detection rates for near-Earth asteroids needed to be increased by a factor of 100 to more completely characterize the population and understand how many of them may one day pose a threat to Earth. The declaration was quickly signed by hundreds of esteemed scientists, physicists, astronauts and Nobel laureates from 30 countries, as well as leaders from business and the arts. I'm Dr. Stuart Clark, an astronomer and journalist, and here to discuss the progress we are making towards that goal. I'm delighted to be joined by Dr. Gianlua Masi, an astrophysicist at Virtualtelescope.eu, Dr. Virkki, an observatory scientist and the head of the Planetary Radar Group at the Arecibo Observatory, Professor Fitzsimmons, an astrophysicist from Queen's University, Belfast, and Dr. Lynne Jones, a research scientist from the University of Washington. Alan, welcome back to Asteroid Day. Now, you were one of the original signatories on the 100 times declaration, back when astronomers were finding about 1,000 or so asteroids a year. Tell me how far we've come towards achieving that 100-fold increase in our detection rates.
Oh, yeah, I mean, it's incredible to think that was only 5 years ago. And the good news is that astronomers have increased their detection rates, but nowhere near 100 times yet. And in fact, you've got to be careful what you talk about. So if we talk about asteroids in general, and that of course includes all the asteroids in the asteroid belt between the planets Mars and Jupiter, then we've found another 100,000 of those in the intervening 5 years. But in fact, we already knew about 680,000 of them. So that we haven't actually accelerated the discovery rate that much. And part of that reason is we have reached the limit of the asteroids out there in the asteroid belt we can find with today's generation of telescopes. But if we look at near-Earth asteroids, the ones that we're concerned about, then the discovery rate has increased over the past 5 years. It's, again, not anywhere near 100 times in the discovery rate, but progress really has been made.
So of those asteroids that we're discovering now, sort of how many can be called near-Earth objects?
Well, back then in 2015, we were finding, as you said, about 1,000 or 1,500 near-Earth asteroids per year. The current research and survey facilities are now finding almost double that. Last year, over 2,700 new near-Earth asteroids were discovered. And even if we just go back a couple of months to April, in fact, we were finding, astronomers were finding up to 9 new objects per night on average. I almost said per day there, but I mean per night, of course. That's when the telescopes work. And that is really tremendous. It's partly due to new telescopes coming online. It's partly due to new cameras being made and installed. And it's partly due to incredibly talented software engineers and astronomers looking at how to improve their detection efficiency.
It's absolutely fantastic how this all happens in such a sort of a treadmill way. It's just relentless, this discovery of new asteroids. Lynne, I wonder if I could turn to you and just ask if you can explain to us, how do we actually find asteroids?
Well, it varies a little bit from survey to survey, exactly what techniques they use. But the general idea is that you take an image of the sky, you don't know what's an asteroid in that one image. You take another image of the sky a little bit later and the asteroid is moved. So if you can detect that motion, then you can find out which ones are asteroids or which ones are just stars or background galaxies. And so depending on the survey, you might take 2, 3, 4 or even more images of the same field of the sky each night, so that you can see that motion and you can pick out the moving asteroids. And almost everybody, actually, all the big surveys anyway, do that detection of the asteroids by using software. So you detect all the sources in an image, you detect all of the asteroids and the stars and the galaxies, and then you try to figure out which ones are moving and which ones are standing still, and you link them together. And the software to do that work, to do the linking, is getting more and more sophisticated all the time. So in the past, there would have been a lot more hand-holding of the software and the outputs, and astronomers would be looking at all of the outputs from these kind of programs and wading through, you know, a lot of things that were not real. And now we're generally at the point where people still make sure that they look at the outputs of their software, but they can look at the outputs, and most of it is real. So things are getting better, things are getting improving. And for when Rubin Observatory comes online in, where are we at now? I think we're sort of about 2 years out from our start. The outputs of this kind of searches will be automatic, and people won't need to go through and intervene and look at so much of the outputs, and it'll be much more automated. And the surveys are getting there. It's like this is part of scaling up to be able to do that 100 times search.
Yes, I understand. And we are going to talk a lot more about the Rubin Observatory later on. But before we get to that, give me a little tour, Lynne, of the major facilities that do this work at the moment.
Oh, well, Catalina Sky Survey is certainly a really important program that's been finding asteroids for a long time, and is still online and finding lots of asteroids. The Zwicky Transient Factory, ZTF, is another telescope survey that's starting to find more near-Earth asteroids. The Pan-STARRS, of course, is still active, finding lots of asteroids. Gosh, you know, actually, I should ask for some more help to make sure I'm being complete, because those are the big 3: Catalina Sky Survey, Pan-STARRS, ZTF. But there are other surveys going on, and
yeah, let's play.
Alan's got one in mind.
Let's play search facility bingo.
Yeah.
Who wants to come in with some more of these big facilities that are doing?
Well,
this work?
I'm going to jump in and put out my hand up for Atlas, as that's
a
project I'm involved with at the moment. Now, actually, to be honest, Atlas is slightly different from some of the facilities that Lynne was just saying, isn't it, Lynne, in the sense that it's really aimed at trying to find these smaller asteroids that are actually quite close to the Earth at the moment, but it does pretty well at finding more distant objects as well at the same time. Not quite as many as Catalina and Pan-STARRS, but it does pretty well.
Atlas.
Who else has got a facility? What's your favorite? Atlas wins. Atlas wins.
Sorry.
Atlas is pretty cool.
Yeah, I like Atlas because the acronym, right? The Asteroid Terrestrial Last Alert Survey Telescope. I mean, it's great.
Yeah, although I do really like how ZTF is pushing the boundaries of what you can do from the ground by looking so close into twilight, and that they found from the ground a near-Earth asteroid that had its orbit completely interior to Venus, which is pretty cool. That was something we didn't think we could do from the ground. So
now this is pretty amazing, isn't it? It seems kind of obvious when you think about it, but it took me a while to actually think about it and realize, of course, there's this whole zone of the solar system that we can't see because it's always in the daytime sky. So who wants to explain that to me much better than I've just explained it?
So it's obviously it's easiest to look at the night sky away from the sun, and away from the sun because of how the Venus is closer to the sun than the Earth. This means that basically things that are straight away from the sun are the easiest for us to find. And if here's the sun, here's the Earth, and there's the night sky. And so things that are outside the orbit of the Earth are easier to find. As you start to try to look interior to Earth's orbit, it gets much harder to see. You're looking closer to the sun, and so you're basically looking at the sky during twilight, and that the sky is very bright and it's very hard to do. And so things that are interior to the Earth's orbit, and especially interior to Venus's orbit, are really hard to see from the ground.
Now, just detecting the asteroids is one thing. But it doesn't stop there, does it? There's a whole load of other work that has to be done just after we just find the asteroids. Anne, I wonder if you could tell us about what that follow-up observations are.
Sure. Thank you, Stuart. So, as important as discovering asteroid is also the post-discovery characterization. Which is something we do, for example, at Arecibo Observatory. So, for example, if you find an asteroid, it gets discovered, usually the optical telescopes discover asteroids by just taking images of the night sky, and they are looking for the spots of light that are moving in reference to the background stars. So for optical surveys, they find asteroids by detecting the sunlight that's reflected off the asteroid surface. With the planetary radar, we generate our own wave, and we are looking for the echo of that wave that gets reflected from the asteroid, and then we are able to compare the echo to the received to the transmitted wave, and that gives us kind of an edge compared to the sunlight reflected from the asteroid. So what it allows us to do is like very precise range measurements, what we call astrometry. So when asteroids are first detected, sometimes they get lost because optical surveys are not necessarily able to tell right at once, like where are they going? And there is always some uncertainty in those measurements. So with planetary radar, we can decrease that uncertainty.
Because it's very important, I think, isn't it, that once we find these asteroids, we keep track of them, so that, as you say, we don't just lose them.
Yeah.
And Arecibo as well, I think, it provides some really unique science about the properties of the asteroids as well.
Yes, like as I explained, we generate our own signal. So radar comes from actually the first radar detecting and ranging, and while we are not detecting new asteroids, but do the post-discovery characterization, the ranging that we do is very high precision, and that first of all, it allows the asteroids not getting lost. It also allows imaging capabilities that are just not possible using optical telescopes. With optical telescopes, you see a spot of light against other spots of light. And with radar, you can actually see craters, or if the asteroid has a moon, some asteroids have moons. We have even seen asteroids that have 2 moons.
So as well as constraining the asteroid's orbit precisely, you get with radar, you get a feel for a bit of what the asteroid is actually like as well.
Yes, exactly. And that's very important. For example, if you're planning to send a spacecraft to that asteroid, you would like to know if something is already orbiting the asteroid, like a satellite that could pose a threat to the spacecraft.
Now, this is not just a job for professional observatories, I think, as well. And Gianlua, you're involved in a network, I think, of private individuals who are making a really valuable contribution.
Hi, Stuart, and hello, everyone. And yes, I must say that the amateur community has been extremely important for the asteroid science since the very beginning, I must say. And I remember when I was younger and I was still hoping to become an astronomer, professional astronomer, and I was impressed to see in my country, in Italy, so many amateurs making a very amazing work, even well before that the digital technology made that job easier. I remember the old film times when it was quite hard to measure carefully the position of an asteroid on a plate. Now it is much easier to do this with a computer. I've been doing this minutes before we started this. And I must say that over the last 25 years, when we really increased our discovery rate, the amateur community also increased its work. And it has becoming harder and harder because larger telescopes are finding fainter objects. And while the professionals can easily hope to have larger telescopes, the amateur community is using smaller telescopes. So it is not easy for unprofessional astronomers to provide follow-up of everything. But I must say they are still doing so. And also, I would like to add that their work is precious, not only for the astrometric follow-up, helping just finding the precise orbit of the object. They are also doing a very important work to provide a physical insight on the object. They can study how the luminosity of the asteroid evolves over the time, the so-called light curve, just telling us how the asteroid is rotating, what is its shape, and in case if there is a binary object there. And of course, the radar people is doing this in a magnificent way, but still the amateur community can really contribute here. And I must admit, Stuart, that I was really impressed to see over the last years how the amateur community could adapt to this amazing development we have seen. They did not surrender. They increased in such an amazing way their ability to offer their amazing work. And it's really a pleasure to see this contribution. It's a bright example how the community can contribute to the professional work.
Okay, so here's a question now. On the face of it, this sounds impossible to answer. The question is, how many asteroids are left to be discovered?
This is a very important question, Stuart, and we had many astronomers in the past trying to understand better the near-Earth asteroid population, trying to model the real near-Earth asteroid population from the observed one, because we have to keep in mind that what we see is just a fraction of the real population, with some limits from the practical conditions we find when observing. And I have seen several studies, even some recent one with estimates, and looking there, we have to say this. The number of asteroids we can expect depends on the size. The larger the asteroid, the easier for us to look, to find it. And basically, we can say that we have found more or less all the asteroids larger than 1 kilometer, for example. And in fact, we find an asteroid of this size just from time to time. It is relatively rare. As soon as we move to the smaller component, we see number increasing. And I have seen recent studies telling that we still can wait, if we consider even the smaller asteroids, 10 meters in diameter, we can still wait to have hundreds of thousands of unknown objects. So really a lot, and a lot of job. This is at least what I know respect of this topic.
Yeah, if I could just join in there, there's another way. Apart from the way that Gianlua was describing it, which is just counting when you look for these new asteroids. How many do you find that you already knew about? If you survey the sky with your telescope, and every time you find an asteroid more than 1 kilometer across, you knew it was going to be there already, then that tells you there can't be many more left to find. And indeed, that's what we find today. But when you go below that 1 kilometer diameter down to half kilometer, 300 meters or so on, you progressively find that you're finding more and more new asteroids as you do your surveys. And that's still the situation, as Gianlua was saying, that we are in today. So we know there are many, many more that we need to discover. And in fact, we can calculate mathematically by looking at how often we find new objects and how often we find objects we already knew about. We can figure out how many there are left to find.
And I believe you put them into size categories as well. You mentioned the 1 kilometer size asteroid, and I believe there's another category that hovers around the 140 meter category. Could you just explain the rationales behind these these categories that you use?
Well, yeah. So the important thing is that we've known from studies 10 decades ago that 1 kilometer asteroids are really dangerous for us. That's kind of around the threshold. If one hits, we could expect global consequences to that asteroid impact, where it wouldn't matter where you are on Earth, you're going to have some effect, and it would be quite severe. If we go down in size, of course, the impact effects are less. And then the computer simulations and calculations imply that as long as you're above 140 meters in diameter, or somewhere around that range, then it doesn't matter what the asteroid is made of, it will still make it to the ground. It will get through the Earth's atmosphere and cause devastation by physically impacting the Earth's surface. And so that's why we have that second limit there. And in fact, anything that passes close to the Earth within 5/100ths of an astronomical unit, which is the typical distance between the Earth and the Sun. Anything that passes that close to us or closer and is more than 140 meters across, we call a potentially hazardous asteroid, because those are the things we really want to worry about. And the problem is that when you find these asteroids, you don't know initially what its orbit is. You don't know really how close it's going to get in the future. So you don't know if it's a potentially hazardous asteroid or not. So it's like asteroid Pokemon, right? You've got to catch them all to make sure you've got the dangerous ones.
So to play asteroid Pokemon, we're going to need new facilities and better searches and faster searches. So what kind of things do we have coming online in the near future?
So I work for a project that is about to come online inside the next few years. It's the Rubin Observatory, Vericy Rubin Observatory Legacy Survey of Space and Time. So this project has been around for a while. Our name used to be simply LSST, but we now are called the Rubin Observatory. And the survey that's being run on that will be run on the observatory is called the Legacy Survey of Space and Time, which is still LSST. And so Rubin Observatory has a big 6.5 meter mirror and a really big camera, about 10 square degrees. So this is bigger than about 7 times the full moon. So the idea is, with our telescope, we go out and we just survey the night sky over and over again. And so every few nights we cover the entire visible night sky twice, so that we can find those moving objects, see those little points of light moving around in the images. And then we can link all of the detections, and we can find near-Earth asteroids, things in the outer reaches of the solar system. As well as a lot of other cool stuff that is relevant for the rest of astronomy. So when Rubin Observatory is scheduled to run for about 10 years, and at the end of the survey, we will have observed about, I'm going to say it will be more than 250,000 near-Earth asteroids, but 250,000 is sort of a reasonably conservative estimate for our total number of objects. And this is objects that are of all sizes in this potentially hazardous size range that Alan was just talking about. Then we will find about 100,000 or so objects that are larger than this 140 meters.
The Rubin Observatory is going to be, the real heavy hitter in this. What else is coming online that will help as well?
So there's also another a space-based project that's in the works, the NEO survey mission, and this is a space-based telescope. So it's a project where the telescope is launched into space, and the great thing about that is because it works in the infrared. The Rubin Observatory will be a visible wavelength telescope. Between the two, we get much better information on the asteroids that we both detect. Also, because they're in space, they can look closer to the sun, so they have less of a problem with that looking into twilight. So they're very complementary surveys. And so these are sort of the two big things coming up.
Yeah, carry on, Alan.
Yeah, no, I was just going to say that, Lynne, absolutely right. I mean, in the meantime, there's going to be some expansion of the current surveys, of course, in the next 2 or 3 years. But one important thing, of course, is as well that the Rubin Observatory will be in the southern hemisphere, which we've been pretty blind to over the past few years. And although some facilities like Atlas are building new survey telescopes down there, smaller survey telescopes, LSST is really going to be great at covering that area of the sky, as well as probably the rest of the solar system as well.
Yeah, well, and I think that for projects, especially projects like Atlas, which is, as far as I understand it, Atlas is very focused on finding things that come close to the Earth, and giving you, because they survey the sky incredibly rapidly, so anything that comes close to the Earth they will see, and anything that's large enough that comes close to the Earth they will see and let us know about. And projects like the Rubin Observatory and the NEO surveyor mission are more aimed at cataloging the overall population of asteroids, and so it's a very nice sort of complementary space. And projects like Atlas are very valuable and fill a different kind of usefulness as well. So,
do we expect more close flybys that we know about and can potentially see as our discovery rates go up?
This is another interesting point, Stuart, because we have seen over the last few years how the discovery rate increased, and of course we are reporting more of these flybys, and often the people are left with the impression that the traffic has increased, like if we are under attack by asteroids. It is not a joke, because every time an asteroid is close to our planet, I receive a lot of email, a lot of messages by non-astronomer people asking for this. And it is important to have them understanding that the situation is absolutely normal out there. It is simply that we are better and better in finding and discovering them. And I hope that explaining this well, we will bring to the community the idea that science is improving our capability to find them and to protect them. It is not an increasing danger numbers. It is just telling us we are better and better in finding them, and also handling the risk of a collision in the future. So I do expect that we will find more and more, and it is important that science communicator and people involved in public outreach will translate this important information in the right way for the non-professional people to understand what is happening out there.
It sounds to me as if the current surveys are in good shape, and that the coming decade will see a real acceleration in our detection rates. So thank you all for your time today. I'm afraid we've come to the end of the panel. I know we could talk about this for a lot longer, but time is upon us. So thank you again for being with us on Asteroid Day today, and for all of your explanations. I've really enjoyed it, and I hope that all of you who are watching have enjoyed it as well. And thank you, and hope you enjoy the rest of Asteroid Day.